Hello Huskies, we are going to talk about features of functions number 4, where you are learning about end behavior, intercepts, and whether a piecewise function is linear or nonlinear. So the objective is I can identify end behavior, intercepts, and linear versus nonlinear piecewise functions. We're going to start off by talking about end behavior. When we discuss end behavior, it's what's happening at the very far end of the spectrum, way out to the right. Like not when x equals 10 or when x equals 100, but when x equals 200 billion. What is the function doing out there? And then on the other end also, not when x equals negative 10 or negative 30 or even negative 200, but when x equals negative 500 million. What is this graph doing? That is end behavior. For end behavior, we're not super concerned with what's happening in the middle of the function, in the center, in the interesting part. Okay, every time I say end behavior, you need to vomit back up two statements that begin exactly like this. So this part, there's nothing to get. You never have to figure out what is x approaching or anything like that. You just need to always write, as x approaches negative infinity, y will be doing something, and then you have to fill in the blank. And then also, as x approaches positive infinity, y, and then you fill in the blank. And that's the end behavior. So this part, this stuff written in red, is what you have to memorize to write down for end behavior. Okay. Oh, sorry, we need to actually discuss what the end behavior is. Basically, if the arrow is pointing down, let's talk about the right-hand side here for a minute. As I go farther out along the x-axis over here, I keep going, wee, forever and ever and ever. What is my function going to keep doing? It's having a bad day. It's just going to keep going down, farther and farther down. So could I make a prediction, like when x is way over here, what's my function going to be doing? Well, it's going to be way farther down. So as x approaches infinity, as I keep going out far to the right, my function y will keep going down farther and farther and farther. And so for this one, as x approaches infinity, y approaches in negative infinity because it's going down. Infinity is not a location. It's an idea that says keeps going forever and ever and ever. So it's going to just keep going, and it's getting more and more negative. Okay, so then basically what I'm saying here is if the arrow is pointing down, then your graph is approaching negative infinity. Approaches negative infinity. Now, let's talk about the other side. As I head off to the left here, as I keep going to the left, my function is just going to keep getting taller and taller and taller, happier and happier, more and more positive. So as x approaches negative infinity, that means as I head far out to the left, y approaches positive infinity for this graph because it keeps going farther and farther up. And kind of the shortcut for that is if the arrow is pointing up, then it approaches positive infinity. And there will be some other situations. We'll talk about those in a minute. Now, there's a shortcut. If you don't want to have to write the word approaches out every time, I am going to let you replace the word approaches with this little sideways arrow. So you could replace all this stuff in red as x approaches negative infinity. That's, yikes, a terrible one. Let's see. Negative infinity. Then y approaches positive infinity. So I just did a shortcut for all that stuff by using that arrow. And then the shortcut for down here would look like as x approaches, yikes, that one's positive, positive infinity, y approaches negative infinity. So that could be the way that you could write that as a shortcut, but you need to know what that arrow means, and it is the word approaches. Okay, so then the second thing we're going to talk about is x-intercepts. And for this particular function, our x-intercepts are where they cross. Well, we've talked about intercepts for a long time, right? Every time you graph y equals mx plus b, we've talked about the y-intercept as where it crosses the y-axis. So let's look at the y-intercept first, because you know what that is. It's the place it crosses the y-axis. And so for this particular equation, it crosses right there. But what might be different for you is that we need to start writing these as a point. And for your x-intercepts, it's going to be where x equals 0, and y for this one would be like negative 1.5-ish. So for your x-intercepts, for your y-intercept, I don't know why I keep saying that wrong, x is going to equal 0, always. And then if you want to find your x-intercepts, then that's where y is going to equal 0. So you might think, what the heck is an x-intercept? Well, if a y-intercept is where it intersects the y-axis, then the x-intercept is where it intercepts the x-axis. And you can have more than one x-intercept. See, we can have this one, and this one. And you'll still be a function. It'll still pass the vertical line test. But if you had two y-intercepts, that would not be a function because it would fail the vertical line test. Okay, so our x-intercepts, let's write those as points. Well, none of these look like they are crossing at very happy places, but we can approximate. So maybe the first one is at negative 3.4, 0. And then we have one that's a little less than 1. And then we had another one, that one might be like 2.1, 0. So those purplish dots, magenta dots, those are the x-intercepts, and then the one on the y-axis is the y-intercept. So those should be pretty simple for you to find. The only tricky part is remembering to write it as a point with parentheses and a comma and an x and a y. Okay, the last thing we're going to talk about is this linear versus nonlinear thing. A linear function, you already know, is the graph of just a straight line. But if it's a piecewise function, it might be made of a bunch of different pieces. And if all the pieces are linear, straight lines, then we call that like a linear piecewise function. So that one's going to look really straight and stiff like zigzag. Nonlinear, it might have curvy pieces. And it might have a straight piece every now and then, but you know, it's going to be made of curves. So that's the difference, linear versus nonlinear. All right. So now we're going to fill in all three of these concepts for a new graph. I've changed the graph at the left. Is it linear or is it nonlinear? Well, it has this curvy part right here. So we're going to say that it's nonlinear. And the intercepts, well, it crosses the x-axis right there at negative 3, 0. And also right there at about negative 1.5, 0. And also right there at about negative 0.5, 0. And then our y-intercept is down there on the y-axis. That looks like 0, negative 1. Okay, so those two things should be nice and simple for you. End behavior. Let's talk about end behavior. For this one, as x approaches negative infinity. Negative infinity, that's to the left, but this function doesn't go on. It stops. There's nothing to the left where this laser is. Nothing at all. And so for this problem, as x approaches negative infinity, what's this function doing at negative 10? What's it doing at negative 200? What's it doing at negative 8 million? It's not doing anything because it does not exist. So that's the answer here. It does not exist. As x approaches infinity, now that's on the right-hand side. What's happening far, far out to the right? As x approaches infinity, well, it's kind of like the airplane idea, like an asymptote. It's coming and it's getting closer and closer and closer, and it's getting closer and closer and closer. This nice gentle curve. And it looks like this graph will be approaching like this asymptote right here. And what is the equation of this asymptote? It's negative 3. Y equals negative 3. So as x approaches infinity, can I predict what my function is going to be doing, like way over here to the right or even farther to the right at 2 million or whatever? Well, I think it will be getting closer and closer and closer to negative 3. Y is getting closer and closer to negative 3. The farther out to the right we go, the closer to negative 3 it'll get. It never will actually get there, but it'll get closer. Okay, let's look at another function. So this one is made of all straight pieces, so that one looks like it is a linear piecewise function. Now the intercepts, okay, let's just, to make this easy, let's say that crosses at negative 1, 0. And this one, I don't know, 1, 2, negative 2.5, 0. And the y-intercept is probably at 0, 1. And behavior, I know that's why you're all watching, because this is the confusing part. Okay, as x approaches negative infinity, what's happening over here to the left? As I go farther out along this x-axis, my function is just going to keep getting bigger and bigger and bigger. It's not going to get out there to negative 2 million and suddenly change its mind and come back. It's just going to keep getting bigger and bigger and bigger. So as x approaches negative infinity, y approaches infinity. And yes, you can use the shortcut if you want to on any one of these. Go right ahead. That's how you would write that as the shortcut. Okay, but off to the right, what's this thing doing? Well, this one's a little different than the function we just looked at, because you're going along, you're minding your own business, and all of a sudden it's like, boom! So I was joking in class that this reminds me of that that cartoon, whatever movie, I can't remember, where he's going along, all of a sudden, squirrel! See the sharp turn right here? He's just suddenly on the squirrel's track. Boom, squirrel. So that's different than the one where it just gently approached negative 3. No gently approaching here. This is just straight up equal to 3. Because it made that sharp turn, and it's going to equal 3 forever and ever and ever. That's not getting off that squirrel's track. Okay? All right, so on your homework, if you are watching this video, you are lucky, because normally I only work out 1 or 2 problems on the homework, but for your enjoyment and educational purposes, I'm going to work out a lot. Almost all this whole homework. So keep watching and you'll get a 10. Okay, this is number 1 on your homework, and behavior. As x approaches negative infinity, in other words, what is this thing doing way over here to the left? Well, it looks like my arrow's pointing down, and so this is a little reminder. If the arrow's pointing down, it approaches If the arrow's pointing down, it approaches negative infinity. Wow. If the arrow is pointing up, it approaches positive infinity. Well, that's good that I had that written down wrong. Okay, so the answer for this then, this particular one, if the arrow is pointing down, well, yep, on the left-hand side, the arrow is pointing down. So this is approaching negative infinity. It approaches negative infinity. And on the right, as we move out this way along our x-axis, our function just keeps going farther and farther down. So then y must be approaching negative infinity again. Both arrows pointing down, it's going down to negative infinity on both sides. Okay, this one's a little less ugly looking. As x approaches negative infinity, on the left-hand side, what is my function doing over here? It was just going along minding its own business. Then it took a jump, and it was like, squirrel! That equals 1. It's just going to equal 1 forever and ever. As you head out to the left, that will always be where y equals 1. On the right-hand side, as you head out farther this direction, what is my function going to do? It's going to keep getting bigger and bigger and bigger. And so it approaches infinity. And behavior for number 3. What's happening on the left-hand side? Is there any function going on over here? No. So for this one, y does not exist. If you would like to abbreviate that as DNE, you sure can. As x approaches infinity on the right, what is this thing doing? It's coming down. It's just gently landing on the runway. It's getting closer and closer and closer to, looks like -4. So y approaches -4. It's not like this one where it was exactly on 1. Nope, this is just getting closer and closer and closer to this asymptote right here at -4. Okay, you can go back and find the x and the y intercepts. Remember that you need to write them as points. The x-intercepts are where y equals 0. That will be on the x-axis. And the y-intercept, there's only one per function. That's when x equals 0 and it's on the y-axis. Okay, let's look at number 7. Look at all this stuff you can tell me about any graph now. So first of all, the domain. This one might be a little bit confusing looking because it does have an arrow on the left, but if you read the problem, if you read the context, then you can see that this is a graph showing the time since the opening bell of the stock market. Well, we're not going backwards in time, so that means that this function actually does just stop right there. There's nothing on the left. So the domain, well, I can use my handy dandy laser pointer. Am I hitting any function values? No, 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 no. Beep! Oh yeah, okay, it's going to keep going forever and ever and ever. So when did I start using x values? Well, my domain started at 0. And when's it going to stop? Never. So that's when you could write it. One way you could write it, you technically don't even need to have this infinity part on here. That would still be right. You could switch that around and say x is greater than or equal to 0. That works also. Now your range. Handy dandy range finder. No, 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 no. Beep. Hey, let's try that again. Beep. Okay. So when my lines are going horizontally, I started hitting my function at about -1.5. And I stopped hitting my function at exactly 0.5. So my range is going to be all the y values between -1.5 and 0.5. Remember, range, y. Y is the range. My max. In order to be a max, it needs to be increasing on one side and decreasing on the other. And I don't see that anywhere. It is increasing, but it never decreases. There's no top of the mountain here. And so you are completely okay to say none. If a function doesn't have something, that's okay. Say none. Now the minimum point is going to be where it's decreasing on one side and increasing on the other. In other words, the bottom of a valley. And we do have that in this case. The minimum point for us is at 3 and -1.5. All right, when is my function increasing? When is it increasing? Well, if I was on a roller coaster ride here, it would start here, wee, chug, 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 and then it would be boring. So it's only increasing for a little while, and that is between 3 and 6. Now remember, it's not ever going to be increasing at exactly that point. At exactly a point. So you don't ever want to put the equal to bars on the increasing or decreasing compound inequalities because it can't be increasing at exactly the point where it turns the corner. It's going to just be neutral or flat right there where it turns the corner. All right, when is this function decreasing? Well, it started going on the downhill, so it started right at 0. And it kept decreasing until I got to 3. Remember, I'm not asking how far down it went. when I ask about increasing and decreasing, I am still thinking in terms of my x values. So I'm thinking in terms of these vertical lines going across here. I started decreasing right at the beginning when my function began, and yet I'm decreasing. You could almost make the beeping sound like with the domain. Beep. That's when I stopped decreasing. So it's in between 0 and 3. When is my function decreasing? It's between 0 and 3. When is my function increasing? It's between 3 and 6. I'm not asking how far down it went or how far up it goes. I'm not asking what is the increase. I'm just asking for when. When. I told you it was going to be an important word for this unit, and it is. All right, let's do x-intercepts while we're here. The x-intercepts where it intersects the x-axis. It's one obvious place is at 0, 0. And the other one, I think it's a little more than 5. You don't have to have the same exact number as me. You can approximate that. And then the y-intercept, there's only one, and it happens to be the same as the x-intercept, but it's 0, 0. Okay, end behavior. It's time for end behavior. What is happening far off to the left on this function? Well, nothing, because it doesn't go backwards in time, and the arrow does not apply to this function. That was the x-axis. So for us, as x approaches negative infinity on the left, y does not exist. There is no function over there. What's happening on the right-hand side as I move to the right? Well, it equals exactly 0.5. It looks like on your graph. My scale is a little wonky on mine, but if you look on your paper, y equals exactly 0.5. Forever and ever and ever. It was going along and all of a sudden, squirrel, 0.5. And it stayed there forever. Okay, on the back, at first you might think these two problems are exactly the same. But they're actually going to have quite different answers because of one word, and that word is the adjective describing what kind of function it is. So if it's a continuous function, or if it's a discrete function, we don't know by just looking at the table if it's continuous or discrete. I have to tell you. And so now I'm telling you that the function for numbers 8 and 9 is a continuous function. That means I can start at one end of the function and trace the entire function without picking up my pencil. That's what makes it continuous. To be discrete, I'd have to pick up my pencil. I can't trace the whole thing. And so that's the difference. The discrete one might be dots, and the continuous one is going to be just a nice continuous line. It doesn't have to be straight. It can still be piecewise, but you can trace the whole thing without picking up your pencil. So to determine the domain for a continuous function, that means that looking at the table, it looks like the smallest number of my domain is 0. And the largest number of my domain is 6. Sorry, I can't squish these in here, so I'm going to kind of write them diagonally. But it looks like my domain ranges from everything between 0 and 6. Remember, it's continuous. That means that I could have the square root of 2 is an element of this domain. 1.414. Pi could be in this domain. 3.141592, whatever, blah, blah, forever. And 1/3 or negative 5/8. Those are all in this domain. Just kidding. Negative's not in here because it's only between 0 and 6. But you get the idea. It includes decimals and fractions. Everything in between 0 and 6. Now, I'm going to just jump down and do the domain of the discrete function next. I'm going to kind of just go in a little different order here. So the domain of the discrete table underneath there, it's not all the numbers in between. It's only the numbers you have listed. 1, 2, 3, 4, and 5. It's just a list. Those are the only 5 numbers in the domain, nothing else. Because it's discrete, it doesn't include anything between there. All right, let's talk about the range. Range, y. Y is the range. So what is the smallest number of the range on number 8 in that table? The smallest number of that range is -3. Can you see that in the table? And the largest number of the range was the 20. And so that, because it's discrete, that means that these values must range in between -3 and 20, and they're probably hitting every single value in between since it's continuous. So that is supposed to say less than or equal to. So it's everything between -3 and 20. But now the range for the table on number 10 and 11, that is discrete. It doesn't include everything in between. So I'm going to write mine in numerical order. I'm not picky. I wouldn't mark it wrong if you didn't. There might be teachers in the future that do mark it wrong if it's not in order, but it's just those y values, 4, 10, 5, 8, and 3, and I put them in order. Okay, what's the minimum value? This is the answer to number 9. Based on the table, identify the minimum value. And so if you look at the table, it looks like we had 0, 2, and then you went all the way down to -3 and then back up to 0. So it kind of went decreasing and then increasing, and that to me sounds like a min. So I'm going to go ahead and say that my minimum point is at 1, -3. Now looking down on the discrete table, is there a minimum point? Well, the smallest y value is 3, so I guess we could say that the minimum point, the lowest value, is at 5, 3, because that's the lowest y value. All right, x-intercepts, going back up to the top table. X-intercepts are where y equals 0. That's going to be true forever and ever and ever in your mathematical life. So where in that table does y equal 0? Oh, it's when x equals 2. Look down to the table below. Is there any place in that table where y equals 0? No? Oh, okay then. There is no x-intercept for that discrete table. All right, going back up to the y-intercept. The y-intercept is where x equals 0, both on a graph and in a table. So can you look on the table and find out where x equals 0? Oh, right there. It's at 0, 2. Is there a place in the table for number 10 and 11 where x equals 0? Oh, you say there's not? Then there is no y-intercept either. And that's fine. That just means there's no dots on one of the axes. Hey, look at all the same answers. Okay, number 12 and 13, you should be able to graph these. You should be able to graph these. Y equals -2x plus 4. Can you graph that? I sure hope so. You go to the 4. You go down 2, you go over 1, down 2, over 1, down 2, over 1. But I know what you're thinking. What is this when x is greater than or equal to 0? Crap. Well, that just means that my domain has been restricted to not include anything over here. Where is x greater than or equal to 0? Oh, it's only on this side. So that means my function is just going to start at 0. And that's what it looks like. I know that this line technically could keep going back there, but my domain has been restricted to just being greater than or equal to 0. So the maximum point then is at 0, 4. That's the highest this thing gets. Is there a minimum? Nope, because it just keeps going down, 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 down forever. Okay, y equals 3 to the x power. Have you ever seen that before? Yes, yes you have. Remember geometric sequences? Remember exponential growth? Does it grow like rabbits? Does it have x as an exponent? It's exponential because x is the power. Say it. Okay, so if you still don't remember how to graph that, make a dang table. X, y. Hey, what if x equals 0? 3 to the 0 power? Oh yeah, the elephant foot smashes it flat. It's a 1. Boom. What if x equals 1? 3 to the first power is 3 over 1 up 3. What if x equals 2? 3 to the second power is 9. Oh yeah, this is an exponential curve that has an asymptote, and then it keeps getting bigger and bigger and bigger forever. That's the graph of that. What's the domain? Well, I can't see any number that I'm not using. Let's do our laser pointer. No, yeah, I'm hitting my function. That arrow would keep going. So beep 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 Oh, heck, it's one of those. All real numbers, every single number you can think of would work as an exponent in that function. What's my range, though? Laser horizontally. No, 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 no. Beep, 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 beep. Okay, so my range is actually going to be all the y's greater than 0. It's never actually going to get to 0, this graph. And that's one way to write it. Another way you could write it is that 0 is less than y, which is less than infinity. There's a y there. Because it's never going to go below where y equals 0. Where does this thing increase? Well, increasing makes me think of roller coasters. So here's my roller coaster. And here's me. Yay! And I'm having fun, but this thing has been increasing a teeny tiny bit for a really long time. Remember that we're always going left to right with our roller coaster. So this thing has been pretty close to level since before I can even remember. But it's going to keep going, and then all of a sudden it's going to get here and go wham! Super crazy, heading straight up. Not exactly straight up, but really steep. So when does it start increasing? I don't even remember. It's all the way back to negative infinity. And when is it going to stop going up? Never. This thing is increasing all the time, forever. It's increasing forever. And another way you could have said that is over all real numbers. When is it decreasing? Never. It's not ever going to go down. We're just going to keep going up. We're not going to ever have fun. This is like the worst roller coaster ever made. So, good luck with understanding your homework. I hope that helps, and I hope you all get a 10 on your homework.